The content of this video, as well as the thoughts, views, and opinions expressed herein, belong to the presenter and do not necessarily reflect the views of Brigham Young University or the Church of Jesus Christ of Latter-day Saints.
We're on the road to talk about more aspects of how science and religion can complement one another, even though a lot of people believe that that never happens. The question is science and religion, are they fundamentally at odds all the time? Well, it turns out that this gentleman right here has made some very important inroads in bringing together many of the aspects of modern science with his theology. And that's really the theme of our series of 4 presentations this week, isn't it? Of course, science and religion share a common goal, and that is to arrive at, to understand the truth about the world and our place in it. And these two endeavors, human endeavors at seeking truth, really need to dovetail well. There's only one truth after all, and those truths need to agree. We're going to begin today with a pop midterm exam since we're halfway through the semester already. Isn't that amazing? Here's your first question. Give it some thought. Okay, who votes for C? I knew you would, because you've been attentive students all this time. Very good. Here's the next question and the last question on the exam. Now, I don't want you writing while I'm talking, so only write during those brief periods when I stop talking, okay? It turns out that there is a good answer to that second question, and it can be fairly brief. Scientists now affirm that electromagnetism, which is commonly called light, especially in former times, carries visual information to the eye and governs the chemistry of the eye and the brain, thus allowing us to not only perceive, but come to understand the world around us that we observe. Today, we're going to talk a little bit about belief in the unseen and how that principle applies not just to religion, as was true in the past, but very much so to science today. We have 5 physical senses, as you know. In Joseph Smith's day, religion claimed that we needed to have faith in the existence of an unseen God, an unseen spirit world, unseen angels, and a long list of unseen things, right? But this is the interesting part. Be aware that in his day, it was a maxim not just in the street, but also in the laboratory, that if I can't sense it, it doesn't exist. Scientists in his day were completely skeptical of any attempt to see, observe, and try to study scientifically anything that you couldn't use your 5 senses to detect. Well, let's see how science has progressed since that day. What about today? Let me just ask you a question. Here's a beautiful vase, and if you were to run your hand over that glass, would you, maybe you've done this, would you expect to feel graininess in that glass? No. And as a matter of fact, that glass is not grainy down to a very high precision. But it does remind us that the idea that things like that vase and the things in the world around us, we believe are composed of atoms today. And that this was true about 2,400 years ago in ancient Greece. We talked about Democritus and how he taught this principle, that the world was composed of atoms, which really derives from the Greek to mean not cuttable. So atoms, in his mind, were the smallest thing that you could find in nature, and that every physical object was made up of these tiny, indivisible, and so tiny atoms that you couldn't feel graininess at our level of existence, even though at a very small level of existence, he's claiming that the world really is grainy, if you will. A lot of time went by before this idea actually got caught up again, because you'll recall in the history of science that it wasn't long after Democritus' day and the day of his colleagues that other Greek scientists came along with other ideas that were more religious friendly, like Aristotle. In fact, the idea of atoms wasn't picked up seriously in science until the early 19th century, along about the time that Joseph Smith was alive. Chemists, as you know, believe in atoms today almost without saying, because when we go in the lab, we can explain what we observe using this model of nature. Not only that, but as a result of believing in the model, the atomic model, we've been able to come up with all kinds of wonderful inventions and products that make our lives safer, happier, richer, more comfortable, maybe a lot more fun, as is illustrated here. I think that if you think about it for just a moment, you'll realize that if we didn't believe in atoms, many of the things that you see around you in this room and that you have on your person wouldn't exist. Atoms, as you have been taught in school, I'm sure, are very tiny. And so it's very difficult to single out a single atom, to pick out a single atom among the many around us. In fact, atoms are of this approximate size, and I've put this in English for American audience, America being the last bastion of the English system on Earth. And you'll notice that this number in inches is much smaller than the limit of the resolution of the human eye. In fact, if we look through a light microscope, you might say to yourself, well, if you want to see an atom, just get a really expensive, powerful microscope and look through it, and you should be able to see individual atoms with your eye. And it turns out that that has not been possible, and theoretically isn't possible, because in fact, the resolution of the best light microscope that has ever been made is much larger than the size of an individual atom. So you can rest easy to know that no human being on Earth has ever seen an atom with his or her eye. This is one of the things that we cannot see that we're talking about today, atoms. Since the early 1800s, we have acted for almost 200 years as if we knew that atoms exist without ever really having seen one. Now, you might say to yourself, well, that really constitutes faith, doesn't it? After all, and by the way, science would possibly use the word faith, but often more often uses the word confidence to describe how we feel about our beliefs in these things that the eye can't see. But is this really faith as taught in our Sunday school classes? I would say yes, because as is common when someone is assigned faith as a topic for their sacrament meeting talk, they'll pull out this scripture almost invariably, right? This is Paul telling us what faith is. Now, faith is the substance of things hoped for, the evidence of things not seen. What could better fit into this category of faith than atoms that we cannot see? In the New International Version, it says, now faith is confidence in what we hope for and assurance about what we do not see. So if a scientist doesn't want to use faith, they can use the New International Version of the Bible instead. In science, confidence, and in religion, faith, starts out small and grows with experience. You remember the parable of the mustard seed. It turns out that faith in science grows much the same way that faith in religion grows. As Christ taught, our faith in him can start out small, but as we put that faith to the test over time, we come to see over and over again that all of our lives and the nature around us testify of the existence of our Heavenly Father and his plan of happiness. And the same is true in the lab. As we go into the lab and our atomic theory predicts that certain outcomes are going to happen because we believe that there are atoms in this petri dish or in this beaker that are going to perform in a certain way. We do it, it turns out exactly as predicted. And so that tends to help us build our faith in that, that thing that the eye can't see as well. Now, science relies on models, not this kind of model, but the kind that we talked about last time. And that is models that are set up to describe something that is unknown to us and perhaps that we cannot see in terms of something that is familiar to us that we can see. For example, the platypus, as we mentioned yesterday. If you wanted to describe a platypus to someone who had never seen one, you could say, the platypus is like a duck, it's like a beaver. It isn't a duck, it isn't a beaver, it isn't even a duck beaver. It is a thing unto itself. And so models typically single out individual characteristics of the phenomenon that you're trying to describe and relate that phenomenon to something that is familiar. Atomic theory has come about because over time, our familiarity with this model and how it works has given us confidence or faith that it is true. We say theory not because it is a theoretical thing, that it is just some pie in the sky idea that somebody had one morning over their breakfast, but in fact, it is a theory, as scientists think of the word theory, a systematic approach to understanding a phenomenon in nature. It's describing something we can't see using features of familiar objects. Why do we have faith or confidence? Well, because it's consistent with the evidence that we have seen in the lab. Also, we have the reports, or we might call it in religion, but it's true in science as well. We have testimonies from multiple reliable sources. We go to class in college and we learn about chemistry, whether we want to or not sometimes, right? And our teacher seems to know what he's talking about or she's talking about, and so we believe. And finally, we believe in theories like the atomic theory because they are predictive and functional for creative action. We can create things with it. We can make things happen that are important to us. So that's in case you fell asleep. I know it's late in the afternoon, and I'm proud of you guys for being here, seriously. At any rate, the reason that we believe in atomic theory more than anything can be summed up in two words: it works. Not because we've seen atoms, but because it works. And it's predictive for creative action, even in silly ways like this. Anyway, how about religion? Why do we have faith in religion? Well, it turns out that the process is really very similar to what I just described in science. We have faith in the existence of our Heavenly Father and his plan and the gospel and so on, because we have evidence. Where does that evidence come from? Well, in part, it comes from the reports or testimonies of multiple reliable sources. It turns out that we have prophets and apostles who can enlighten us in ways that help to reinforce our understanding and belief in things that we cannot see. And it's predictive and functional for creative action, like that kind of creative action right there, that pays off so well for so many of us as it has for me. It works. Well, I think it's a fair question to ask ourselves, when we say we know something, what does it mean, and how do we know? We think we know that there is helium in that balloon right over there. See those red and orange balloons over there? I bet you the minute you walked in the room, you thought, oh, those are helium balloons, right? Well, there is evidence that helium exists because we have reports or testimonies from hundreds of thousands of peer-reviewed journals. And every one of those is like the piece of a puzzle, comes together, and it gradually, as more and more pieces build up, we see the picture more clearly and more clearly. It's predictive and functional for creative action in the sense that we can do creative things like this that I'm sure you've done every time you see a helium balloon. You can't have a helium balloon in the room without doing this, right? So while I'm struggling trying to get this out of here, let me make you aware that I'm going to speak with helium in my lungs, and you've heard this before. I would love to be able to speak with something heavier. In the past, I've done so, and I'll tell you about it in a minute, but are you ready? Okay. Now, if I keel over, just haul me out, and my wife will take over. Oh, it's not coming out. Oh.
And that's what it sounds like when you have helium in your lungs.
Yeah, that's lovely, isn't it? I was going to also illustrate that we know of physical materials in chemistry that aren't just individual atoms filling balloons like this, but also compounds, so-called, that exist in the form of molecules, the carbon dioxide molecule being illustrated for you there on the screen. Now, not all objects that we observe in nature can we see with our eyes. You didn't see anything coming out of this balloon, did you? But there was helium in the balloon. It's not visible to our eyes because it doesn't reflect light and it doesn't absorb light. And the same is true with what's in this box. This box was filled earlier on by our friendly lecture prep people with dry ice, which is solid carbon dioxide. But it's been evaporating gradually, or subliming actually, sublimating if you want to say it that way, for the last little while. And the box is now full of carbon dioxide. Carbon dioxide, you wouldn't want to breathe it in the way I breathed in the helium, because it would asphyxiate you as it asphyxiates this flame. We know there's carbon dioxide in there because we have learned through experience that dry ice is made of carbon dioxide, and that if you expose it to the air at room temperature, it will sublimate and come up into the gas phase. But we've also learned that it is denser than air, and so it will simply sit in the box as long as we don't disturb it. And all kinds of things that we know about nature simply because of the experience of ourselves or others. And this experience builds up over time to give us confidence or faith that we have a true representation and understanding of the natural world. I mentioned to you that there were heavier compounds as well. One of these is called sulfur hexafluoride, which is also a gas, one of the heaviest gases that you can find around. And it consists of a sulfur atom and 6 fluorine atoms bonded together in the shape that you see there on the screen. As a matter of fact, these collections of atoms have a name. They're called molecules, and molecules range in size from relatively small ones like carbon dioxide that you saw in the previous slide, and also sulfur hexafluoride that you see here. Helium is very light. It's a very light atom. Some of the atoms in SF6, all of the atoms in SF6 are kind of intermediate in weight, but you collect them together like this, and the total weight of each individual particle is quite high. And so we're going to pass around to you right now a helium balloon and a balloon filled with sulfur hexafluoride. And you can see the difference between the two. As a matter of fact, Isaac, if you'll give me one of those SF6 balloons, you've heard of a lead balloon? Well, there it is, okay? And these folks are going to allow you to, please don't break the balloons, especially the SF6 balloons. It is not particularly friendly to human beings. And actually, in our classes years ago, we used to breathe in sulfur hexafluoride and speak just as I did with the helium. And it made you sound like Darth Vader. You know, it just kind of sounded like that because the higher molecular weight of SF6. But one of the points I wanted to make with this fun demonstration is simply this. You look at a helium balloon like one of these and the SF6 balloon, they have the same number of particles in each one. They're roughly the same number of helium atoms in one of the helium balloons as there are SF6 molecules in one of the SF6 balloons. The difference, the reason that the SF6 balloons are heavier is not because there are more particles in the balloon, but because each particle weighs more. Okay, does that make sense? Well, there's a little excursion into chemistry just for fun. I wanted to make you aware too that these atoms, as we mentioned yesterday, are held together by forces. And they are the very forces we spent pretty much all afternoon yesterday talking about. Do you remember that word I told you was going to be on the final exam? What was it? Electromagnetic. The atoms in SF6 and in CO2 are held together by these electromagnetic forces. Those are the same forces that hold the individual atoms together. The electrons and the nuclei are held together by electromagnetic forces. I also wanted to point out that some molecules get really big, like DNA. This is a tiny section of a DNA molecule. Well, actually, this is a model of a tiny section of a DNA molecule right here. And you see lots of phosphorus atoms and oxygen and carbon and hydrogen and so on. Okay. You'll remember that we can identify which atoms we're looking at using the light that is emitted from these atoms if they're excited. And this whole system, this process, everything I've described to you now comes about as a result of 200 years of study by scientists as to what atoms are and how they behave, what molecules are and how they behave. All of it consistent with atomic theory. And our faith in this theory has built up over time, just the same way that your faith in the Lord Jesus Christ is built up over time through the life experiences that you have. Here's an interesting demonstration also. What you're seeing here is called a flame emission. Methanol is burning, and as copper on the left or strontium atoms on the right are pulled up into the flame, their electrons are excited, and then when the electrons fall back down, they give off light of specific wavelengths. In the case of strontium, red, and in the case of copper, green. Makes for a nice Christmas decoration. Although I wouldn't put it right under your Christmas tree, just word of warning there. But it turns out that all these individual atoms on the periodic table have their own interesting characteristics. They're all little worlds and individual things of their own. I said that no one had ever actually seen an individual atom, but there are ways to detect the presence and the shape of individual atoms that have popped up just over the last few decades. Here's the result of one of the first images that was made of copper atoms. And it was done using a so-called microscope, but not the kind of microscope you look through with your eye. In fact, the word is almost a misnomer, because really the way this works is kind of fascinating. It's amazing that it actually works at all, as far as I'm concerned. Remember those old vinyl records we used to listen to? And the needle would follow the groove, and the bumps in the groove would generate the sound that you hear, the beautiful Vivaldi or whatever you're listening to. It turns out that this kind of microscope works exactly the same way. There is a tiny needle tip that is scanned back and forth, hence the word scanning, scanned back and forth over the surface of a material, in this case copper. And as it does so, it rides up and down on the atoms individually, okay? And that generates an electrical voltage that is measured and so on, and an image then is created from this process. And that is considered to be the first actual visual representation or experimentally derived representation of the way atoms look. And this system has been developed to the point where with this little tip, you can actually pick individual atoms up and move them around on the surface of a material. And this is an actual picture. It's not a representation or anything like that. It's an actual picture of individual atoms, not picture like a photograph, but picture taken with a scanning microscope like this. And these are Japanese kanji that, according to the book from which I stole this picture, says atom. I don't know whether anybody speaks Japanese here and can confirm that. Does it? Oh, it's Chinese? They lied to me. That's okay. As long as it says atom, that's the main thing, right? Okay. Well, the world of atoms is so small that any object large enough for us to actually see is composed of just an enormous number of atoms. And this rivals the enormous numbers that we talked about yesterday or 2 days ago in the number of stars in the known universe. In fact, in a single grain of sand, you might find this many atoms, which is about 2 times 10 to the 19th atoms. And you recall that that's on the order of magnitude of what we talked about in terms of the number of stars in the known universe. That is kind of one way of seeing that there are these extreme ends of the spectrum in terms of size. There are all these atoms in a single grain of sand, and there are all these grains of sand that represent the number of stars in the known universe. Almost as many. A universe of atoms in every grain. Atoms are typically not just sitting still. You know, in a chemistry textbook, you look at the pictures that are supposed to illustrate the structure of molecules and so on. You get the idea that atoms are just solid, sitting there, not moving. They're active, alive little creatures that do all kinds of interesting things on their own. There are very large molecules, as I mentioned before, and we use X-rays to come up with the individual structures of these things. Chromosomes, of course, are made of long strings of DNA with other proteins there together with them. One molecule of DNA hosts millions of atoms. And what's amazing, this is almost mind-boggling, I think. It's amazing to think that in the nucleus of every cell in your body, those cells are pretty small, right? The nucleus, there are molecules of DNA that are 6 feet long. Just one molecule of DNA. In fact, because you have so many cells in your body and so many DNA molecules, in one human being, there is enough DNA to stretch from the Earth to the sun, which is 92 million miles, 68 times. Doesn't that just blow your mind? Even though, I'm going to skip that one. I'm going to go right to this because we saw yesterday just a brief clip from the video that you're going to see right now to illustrate the awesome nature of this small world that we cannot see. Here we go. Isn't it just fascinating to think that these kind of processes are happening inside our bodies all the time? I'll get to questions at the end, if I could, please. That is, no, thank you for asking that. That is computer generated. We don't have any kind of machine that will allow us to actually look with our eye or even with a microscope or a camera to see what's happening. We know by a tremendous amount of work, tedious, systematic studies of how this all functions, the accumulated results of decades of work by thousands and thousands of scientists to go into understanding how just this one little process in a living system works. But it's amazing to me that these systems are so complex and function as well as they do. So the atom, in the 1800s, it was considered to be solid balls. But by this century, we realize that the atom is 99 point whatever number of nines empty space. This is because the nucleus of the atom is extremely small and hosts more than 99% of the mass of the atom. The electron cloud that is around the atom is almost like nothing. And this takes us now onto a realm, a topic related to what the eye can't see that is kind of beyond atoms themselves and into a topic about space itself. Okay, so the atom itself consists of almost nothing in terms of volume and mass. But that's true of the galaxy as well. So we look at the extremely small, and it's mostly empty space. The galaxy is almost all empty space as well. You know that the closest star to the sun is 4 light years away. 4 light years is a long distance. There is a huge volume of nothing between us and the next star. And that is true of all stars. And then, of course, our galaxy is 2.5 million light years. So our galaxy is about 100,000 light years across, okay? And the next galaxy, which is Andromeda, the next big galaxy, which is Andromeda, is about 2.5 million light years away. And so between our galaxies also, there is a tremendous amount of just empty space. So it turns out that the universe is mostly empty space. What does that mean about you? Well, first of all, it means that you're 99 point so and so and so and so empty space. Don't be offended, okay? But that's true. Gives new meaning to being empty-headed, doesn't it? Well, none of this was known. None of this about atoms, molecules, DNA, none of this. The idea that the atom is structured in such a way that it is mostly empty space, not known in his day. The idea that there are multiple galaxies and that there's empty space between stars that are so far apart, and so on. Pretty much everything we've talked about today, we have learned, we as human beings have learned on this planet, these things just in the last couple of 100 years. Nonetheless, it's interesting that Joseph Smith makes this claim. This is in D&C 88. All kingdoms have a law given, and there are many kingdoms, for there is no space in which there is no kingdom, and there is no kingdom in which there is no space, either a greater or a lesser kingdom. And unto every kingdom is given a law, and unto every law there are certain bounds also and conditions. Behold, all these are kingdoms, and any man who has seen any or least of these has seen God moving in his majesty and power. Notice, kingdoms are full of space, right? And there's no space in which there's no kingdom, and no kingdom in which there's no space. And when we see these things, we are struck awed, A-W-E-D, by what we see and what we don't see. What we don't realize is that all these kingdoms are full of empty space. And yet, when I speak of kingdoms, of course, I am speaking in the broadest terms, speaking of galaxies, of stars, of Earths, of people, of atoms, of molecules. You look at all of these things from the 21st century scientific point of view, they're full of empty space. In Joseph Smith's day, nobody knew that. Everybody assumed that if there were atoms, and that was not even clear at the time, that they would be the kind that Democritus described in 400 BC. And that is hard, indivisible objects that touch one another, and therefore there would be no empty space between them. What's Joseph teaching here? He's teaching something that in his day actually didn't make a whole lot of sense. What do you mean? And what are these kingdoms that you're talking about? And what do you mean they're full of empty space? That doesn't make any sense at all. In fact, that flew in the face of what science was teaching. Here's a real, in my opinion, a real testimony of the fact that Joseph was being taught by beings who knew a lot more about the world than the scientists of his day. In fact, DNC 88 is called the olive leaf plucked from the tree of paradise, he said. And it really is. It's full of beautiful allusions to truth, and truths often that we understand better today in science than they did in his day. Did Joseph Smith know any of these things about atoms and galaxies and all this empty space? Not a word. In fact, in his day, that would have been considered ridiculous. Keep in mind, he says, for there is no space in which there is no kingdom, and there is no kingdom in which there is no space. This seemed like nonsense at the time, but not anymore. Also, he says, in the dispensation of the fullness of times, when God will gather together all things that are in heaven and all things that are upon the earth, even in one. Those things which never have been revealed from the foundation of the world, but have been kept hid from the wise and prudent, shall be revealed unto babes and sucklings. In this, the dispensation of the fullness of times. Our children and our grandchildren are learning things in their science classes in school that the wisest and most well-educated people in history before 1800, roughly, had any idea was true. Just as this quotation explains. So the unseen world of atoms and the parts of atoms is a testimony of Joseph's insight into the true nature of nature. Speaking of atoms, there's one. Science, like religion, asks us to believe in things that we cannot see and that may seem counterintuitive. Notice that that was true in religion also in his day, and is true even today. Brigham Young said that every discovery in science and art that is really true and useful to mankind has been given by direct revelation from God, though but few acknowledge it. I just put this up. We've seen this before, but I wanted to remind you that our attitude, by our, I mean the LDS perspective on learning and science, is somewhat unique in the sense that we believe that God inspires scientists to come up with a lot of these things, because in the latter days, in preparation for the coming of his millennial reign, he has promised to reveal even to babes and sucklings things that have been kept hid from the foundation of the world, and that he's going to pour out this knowledge and understanding about the world to everyone on the earth, and that includes humble scientists like the ones that you know. Well, let's talk a little bit more about what we can't see, but is being revealed in the dispensation of the fullness of times. Did you know that you are swimming in an ocean of radiation and particles that you can't see or perceive in any way? The current scientific model of the world is that all this material we have is made up of little particles, atoms, but even the atoms themselves are also made up of little particles like protons, neutrons, and electrons. There are about 10 to the 80th of these in the universe, as estimated, quite a few, as you can see. But there's another kind of particle that maybe you've heard of, maybe you haven't. They're called neutrinos. They are almost massless. Their mass is so small that for a long time, scientists couldn't figure out whether they really had any mass at all. But they move very close to the speed of light. And there are millions of them, trillions of them, passing through you right now, every second. And you don't even realize it. Now, think back to what we said about empty space. Is there room for anything to move through you? You betcha. You're mostly empty space. There's no problem at all with neutrinos just zooming on through you. And if they're not going to interact with any of your particles, any of your atoms or molecules, you'd never know that they were there. Turns out they are. Isn't that interesting? Neutrinos have no charge, almost no mass, and they don't affect us at all. They just pass through the Earth unaffected as well. They just pass right through the whole Earth. It takes a detector like this to be able to actually detect even one of them, because they don't interact with normal matter very well. This detector has 50,000 tons of water. It's 1 kilometer underground, and maybe it'll detect 1 neutrino a day. Now, just to put this into perspective, you know what that is right there? That's a boat. There are 2 people in that boat floating around. This is not a detector like you would put on your shelf. Okay, this is a detector that is the size of a gigantic building. That's what it takes to be able to detect these neutrinos. How about light? We've already talked about how so much of light we didn't even know existed until Joseph Smith's day. Joseph's claim was that there is no such thing as immaterial matter. All spirit is matter, but it's more fine or pure and can only be discerned by purer eyes. We talked about that yesterday at some length. But it also applies to what we're talking about today, doesn't it? In the sense that he's talking not just about the visible light that we can see, but all those other kinds of light that we now know exist and didn't know existed in Joseph Smith's day. Seeing is believing. Well, that was true in Newton's day back in 1700, in the sense that all he had available to him was his eyes. And so anything you see with your eyes, you would assume did not exist. But in fact, there were lots of other kinds of light that were available. Since the 1800s, we have come to realize that all that time they realized they had been observing only a tiny part of all the light or electromagnetic spectrum that there is out there. And so this little spectrum of light is a very narrow part of the entire electromagnetic spectrum. And you can imagine how much we're missing because our eyes miss all this other radiation that's floating around all around us, and we don't even know that it's there. Since the 1800s, we've come to realize all that. Oh yeah, I already said that. We mentioned yesterday that light in science is a key, but it's true also in theology, isn't it? And this is a subject that we spent a little time from Parley P. Pratt's book, The Key to the Science of Theology. And if you want to learn more about that, I'll refer you to my own book. Well, what else does science ask us to believe that we can't see? Okay, it's time to wake up. If you want to pass this class, try this pop quiz. This one has yet to be actually observed, but I'm predicting it. At any rate, the answer here is a hypernova. And a hypernova is what generates what we call a black hole. It's really just a big supernova, okay, hypernova. I don't know how many prefixes we're going to have to use over time as we keep inventing and discovering more and more powerful and big things. What's inside a black hole? Well, there's something else we can't see. It's called a black hole because we can't see inside it because it's so dense that even light can't escape. We don't know what's in there. No light can escape. And there are supermassive black holes that would boggle your mind at the center of each galaxy. They typically have millions or billions of times the mass of our own sun. How do we know they exist? Well, a couple of reasons. Up until just a few years ago, no one had been able with a telescope to actually see a black hole. But this picture was taken in 2017 using 8 telescopes. Now, they're not visual telescopes, so we're looking at radio telescopes here. This is a black hole 53 million light years away from us. That means it's in a different galaxy, right? Okay. And it has 6.5 billion solar masses. The biggest black hole that has been observed up to this point has 66 billion times the mass of our sun at the center of a galaxy. We believed in black holes long before we could take any pictures of them, because we saw a supermassive one at the center of our own galaxy. Did we actually see it? No. We deduced that it must be there because we observed the orbits of stars around a point in space that had no apparent object in it. And these stars at the center of our galaxy were moving extremely fast in extremely tight orbits, and the only possible conclusion was that there was a black hole. But here's the rub. Turns out that very recently, oh, and by the way, it has 4 million times the mass of our sun, the one at the center of the Milky Way galaxy. Can't really see it, but we're expected to believe it with good reason. But now we have an even better reason, because it's only in the last couple of years that we have come up with a, again, radio telescope picture of the black hole at the center of our own galaxy. So you should feel some measure of ownership in this black hole. That's our supermassive black hole right there. That's the hole. And what you see around it is the accretion disk of material that's falling into it and being spiraled so fast around the black hole that it heats up from friction to the point where it's giving off light and even X-rays. So there's something else that science expects us to believe in that we couldn't see before, but it's really interesting. Here's a good cartoon about black holes. It's a black hole. Wait, what's all that debris? It looks like, hey, it's my letters to the editor and my movie script submissions and all the ideas I've ever put in the suggestion box. You'll remember that Newton had a model of gravity. His model was that gravity is a force between, say, the Earth and the Moon. The problem is that he didn't know what that force was. There was no physical object representing that force that you could look at. And so he was criticized that this was kind of a spooky action at a distance. And even though his model of gravity was accepted and taught for 200 or more years, this question was never answered. And people always were worried about this because it seemed like it was magic. Well, the solution came along thanks to this gentleman here again. The solution to this dilemma about the force of gravity came along because Einstein proposed in 1915 in his general theory of relativity that space itself was malleable. And if space itself could be deformed, then as material moved through that space, the trajectory of that material would seem to curve. And that was the reason for what we observe to be gravity, not this mysterious force that Newton had proposed. It's very difficult for us to imagine what a four-dimensional world would look like. And I'd suggest that there are videos on the web, on YouTube, that you might, if you're interested in this, that you might go to try to come to some level of understanding of what he's talking about here. But just take it on my word as part of our presentation about things you can't see. This model of warped space-time has now become accepted as the reason for what we observe as gravitational force in nature by science. And we have to kind of accept it, even though we can't see this fourth dimension that Einstein talks about. Okay? So I'm going to skip over these. I was going to try to explain it to you, but I probably would have made a mess of it anyway. So you'll just want to remember that Newton's gravitational forces have now been replaced by Einstein's four-dimensional model, and that this represents one more aspect of nature that science asks us to believe in, even though we can't see it, which is the theme of our discussion today. Okay. How do we know? Well, if gravity were a force, as Newton predicted, then light should not be affected. But it turns out that experiments were done to demonstrate that the light from stars coming past our sun followed a bent path. And that was the experiment, that was the observation that essentially clinched Einstein's new model of gravity. We saw light bending around the sun. For 4 years, when Einstein actually proposed this new model, people were pretty skeptical. But an experiment was done in 1919, 4 years later, that showed this curved path of light from a distant star around our sun. And that proved the model to everyone's satisfaction, and ever since, there have been additional pieces of the puzzle that have been added to observations that underpinned Einstein's model. And this constitutes the kind of faith that we were talking about when we started today. That made Einstein very happy. But guess what? There are more things that science asks us to believe in that we cannot see. That's only the tip of the iceberg we've talked about so far. But don't worry, I won't be talking much longer. There are two more things that science asks us to believe that I'd like to just mention to you. The first is dark matter, that was first proposed in the late 1900s, not that long ago in our lifetime, okay? There's a picture of it right there. We can't see dark matter or perceive it. Why was it proposed? Because there isn't enough matter in any galaxy to hold the galaxy together. And so it was proposed that there must be more matter in a galaxy than we can see with our devices. We can look out there with microwaves and radio waves and visible light, and it doesn't matter, we can't see it. But it must be there. We deduce that it is there because there is enough matter in the galaxy that the galaxy doesn't just spin apart and all the stars fly away into outer space. We can't see or perceive this so-called dark matter. We don't know what it is. It accounts for much more mass in the cosmos than all the matter we can see. Now that's important to know. There is, according to science right now, despite all we talked about on Tuesday, about the vast number of stars in the universe that we can see, the proposal now in science is that there is dark matter in the universe, much more dark matter in the universe that we can't see, and we don't know anything about it. It must be there. Dark matter accounts for the extra gravity that we can see, enough to hold the galaxies together. It also accounts for the fact that light coming from distant galaxies is often distorted by the presence of galaxies in the foreground. Dark matter accounts for the extra gravity that we can see. And remember this picture of the arrangement of galaxies in the universe in this kind of honeycomb or, this fashion where there is so huge voids of empty space. The bottom line is this, and this is a challenge, I think, to us. It's a challenge to our faith, if you will, in science, and that is all this time, from the time immemorial, from the time of the Greeks, from the time of Newton to 2 decades ago or 3 decades ago, All we have been studying is 5% roughly of all that there is in the universe. So scientists apparently are never going to run out of things to study, because all this time we've been studying like 5% of what there is in the universe. We've still got the other 95% to go. Isn't that great? Dark matter doesn't interact with ordinary matter at all, except in terms of gravity. In fact, a dark matter dinosaur could waltz through this room right now and we wouldn't know it. Remember, you're 99.99, you're empty space anyway. So a dark matter dinosaur could waltz through this room and you wouldn't even know it. In fact, there may be whole worlds of existence in this room made of dark matter, things going on right around you that you don't have any idea are there. Uh-oh, there's more. Not only do we have dark matter to worry about, but in the late 1900s, it has been found that there must be what's called dark energy in the universe. Dark energy accounts for the fact that, remember we talked about how in the 1920s, Hubble discovered that there were more than one galaxy, but also that the galaxies were doing what? Moving apart. It turns out that they're not moving apart uniformly over time, but they are accelerating in their motion. They're moving apart faster and faster and faster as time goes by. The only way that science cosmologists have been able to explain this is to propose the existence of what is called dark energy. And there's a lot more dark energy, supposedly, than there is dark matter. So the universe is expanding faster and faster. It's kind of the opposite of gravity. It's kind of like anti-gravity for stars and galaxies. There's a picture of dark energy right there. We can't see it or perceive it. We don't know what it is. It accounts for much more mass and energy in the cosmos than all the matter we can see, plus all the dark matter we don't understand. Science today is asking us to believe lots of things that are difficult to swallow. There are kinds of matter and light that we can't see with our native senses. Most of matter is empty space. There are kinds of matter that don't interact with our kind of matter by electromagnetism. The universe is really four-dimensional. Most of the universe is dark energy. If that's not faith, I don't know what is. How do these claims compare to those made in religion? Well, I think that's obvious. In religion, we believe we have good reason to believe in all kinds of things that can't be perceived by the natural eye. But the same is true in science. In Joseph Smith's day, religion made the claim that that we could have faith in the existence of an unseen God, a spirit world, angels, and so on. And in his day, science made the claim, and the emphatic claim, that if I can't sense it, it doesn't exist. This problem now has been resolved. In whose favor? Guess what? In the latter days, both science and LDS theology teach of worlds hidden from our natural senses, but that we believe to be as real as anything we can perceive directly.